Yeah. Good morning, everyone. I'm Praveen, a senior physical design at Intel India Private Limited. Beside me, we have Vinaya Gudeangadi, who is an associate in design manager at Intel India Private Limited. So today, the talk will be about an effective implementation of SoC feed-through in an IP with multiple instantiated blocks. So when we say multiple instantiated blocks, we implement one block which is getting instantiated multiple times in a design. So here is the agenda. We will go over introduction, problem statement, proposed solution for the problem we are facing, and we can go over result, comparative analysis, and finally the conclusion. So to begin with, the designs are becoming compact day by day. It is important to save the area of the SoC. So at the SoC, right? Nowadays, SoCs are implemented with the IPs abutted next to each other, and there are channels are getting used to connect the between the different IPs. Okay, just so if you refer to the below diagram, this is the channel-based connectivity where an SoC is getting implemented with the different IPs. And if there's a connection between the IP1 to IP8, they have to go through these dedicated channels. So the problem here is when the interconnect signals are too high, using these dedicated channels to carry signals between the IP can have significant impact on the total SoC area. These channels, right? They only carry the signals. They doesn't have any logic associated with them. So due to that, there is an inefficient way to utilize the design area. Instead, we can utilize the IPs themselves to carry these feed-through signals in a novel approach to save SoC area. So if you refer to the next diagram here, where this is the feed-through based connectivity, where we are completely eliminating the channels over here, and we are taking all these signals over the IPs. So if IP1 talks to IP8, it's coming over, it's crossing over like IP2, IP5, and then reaching IP8 through the other IPs. Okay, so these IPs are self designed. On top of it, we are taking extra burden of these SoC feed-throughs. But here we are able to eliminate the extra area to be accommodated for the channels. So the main challenge arises when introducing these signals to IPs that contains MIBs, multiple instantiated blocks. For example, if you refer to this diagram, we have R partition where it is getting instantiated four times, like R0, R1, R2, and R3. Similarly, there is a Q partition which is getting instantiated two times, Q0 and Q1. So here the Q partition was placed parallelly, and here the R partition was placed serially, right? So now, when while taking these SOC feed-through lines over these partitions, when we give a free hand for the tool, what we observed is tool has not performed efficiently in creating pins for these SOC feed-through signals, where the MIB partitions are placed in parallel fashion. So, I mean, consider the case where if we have to take a 6K SoC feed-through signal, which has to go over Q0 and Q1 partitions, where ideally the intention is to share between these two partitions, where SoC signals, right, need to be connected 3K signals over here and 3K signals for the Q1 partition. But when tool is trying to create when trying to do a port punch on these MIBs. So initially it will get started with Q0 partition where it creates 3K signals. I mean, it port punches 3K ports over in Q0. Because it's Q1 is also an MIB, it creates similar 3K signals over here, right? And then when it comes to these signals, so it creates an additional of 3K signals in Q1 partition now, which will again reflect in Q0 partitions also. Okay, so instead of sharing 3K signal each between these two partitions, it's trying to create the additional ports, which is in turn creating the routing issues. And because these signals travel a long distance and it creates a crosstalk impact also. Especially we see a lot of crosstalk impact in the lower nodes. So the proposed is a solution for creating SoC feed-throughs in the parallel arrangement scenario of the MIBs. So here you can consider a case where we have m number of SoC feed-through wires which are going over this particular IP. Okay, so there'll be a signals which will going from left to right to an IP, as well as in return we will have a signals from right to left as well. So this is where L2R represents the signals which are going from left to right, and R2L represents the signals which are going from right to left over that IP. So the main important guideline here is for the proposed solution, we need to make sure the number of inputs and output signals passing through these each instance are same. So when we say that, right, the SOC signals which you are planning to go over these particular IPs which have MIBs, we need to make sure they have equal number of inputs and output signals going over these each instance of MIB. And the order of input and output signals in these instance will be same as per the physical perspective. Okay, so once we have this, so the methodology, first what it does is it segregate the signals, which, I mean, whatever SOC signals we have, right? It will try to segregate the signals which are actually going from left side to the right side, and also it tries to segregate the signals which are coming from right to left. So, in our scenario, we have two MIBs. I mean, we're considering two MIBs, right? So, what it does is now it will segregate these signals into half. Like the signals which are coming from left to the right side, uh, it will be divided into two, and the signals which are going from right to left, again it divides by two, and it creates these many ports in one of the instance, say Q0. Okay, so the moment when you create these many ports in Q0, the similar number of ports will reflect in Q1 as well. And after creating the corresponding input and output ports for this one partition, then we'll be creating the nets connecting those input and output ports from L2R, as well as the signals which are in the reverse direction from R2L as well. So far what we're discussing is at the power level, partition level, where we are trying to create the uh, optimal port creations which are necessary. I mean, which can be shared between these two MIBs. So now we are shifting our focus to the IP top level connection, where now, as per the previous slide, we understood we have created the connections within the partition. Now we are trying to do a connectivity at the IP level, right? So now, if you consider the partition of Q0, now we have in the first step we have already segregated what all signals to be connected to Q0 and what all signals to be connected to Q1. So here, the signals which are traveling from left to right. So first the input signals will be connected to the left side of the partition, and then the corresponding the output net on the right side, we will create a new net and we will be connecting to the boundary of this IP. Similarly, the signals which are coming in the other direction from the outside world to this IP, we will be connecting right side as an input port over here, and the corresponding output net will be connected to the SOC signal on the left side. So similar, so here, right, as we consider the example of 6K signal, so this manner we are able to connect almost 3K signals for this Q0 partition. And similarly, uh, the Q1 partition, which is an MIB, we are trying to reuse all those signals by connecting the leftover signals, leftover SOC signals for to the Q1. So in the what we done over here, right? In the similar fashion, we'll be connecting all the signals from left to right on the input on the left side of the Q1. Similarly, the output ports will be connected to the outside world, and the signals which are coming from the outside world will be connected to this right side of this Q1, and similarly, corresponding outputs are connected to the SoC feedthrough lines. So, with this methodology, we are able to use uh, the SoC feed-through lines crossing over these MIBs effectively. By doing so, right, instead of dealing with 6K nets in one partition, because as said, right, we will be implementing only one partitions, which is just getting reused as a Q1 instance over here. So instead of dealing with 6K signals, we have to deal with only 3K signals in this partition. And I mean, these SoC feedthrough signals are also like extra lines which are going over this partition, apart from the intended design related to this queue partition. So it's an overhead. So by doing so, now the results are here. So with the traditional approach, where we gave a free hand for the tool, so tool has created almost more than 6K bytes, and then at the play stage, right, we are seeing almost 0.12% congestion. So congestion in the lower nodes, it's quite significant. I mean, it's kind of a bad number. And this congestion number translated to almost 900 shots towards the end of the route design. When the actual routes come into picture, we are seeing a lot of DRCs and lot of, rule violations. And it's also, I mean, if you see the timing number, right, it's also bad. So it took time for us to fix this the timing. And if you see the WNS over here, it's the main contributor here is the crosstalk, because all the 6K lines which are going over these partitions are running long distance, and there is a lot of crosstalk impact on all these signals. With the proposed approach, where we are trying to cut down these number of signals by 50%, we see that in the result where congestion has come down significantly to 0.03%, where after the routing of the design, we see it has come down to 150 shots, and the DRC count has significantly come down. And if you see the timing summary, the WNS has come down to 87 PS now with 13 NS of total TNS, and the number of paths which we have to deal with has come down more than 50%. So a deep dive into comparative analysis. So if you see the congestion, right, the congestion is mainly, I mean, it tool try to check for the availability of the tracks. Wherever it's not available, that's where, I mean, it says that, okay, this is the percentage we are hitting the non-availability of the routing resources. So this way, right, if you compare because the routing directions will be both in horizontal as well as the vertical direction, in a if you compare the horizontal directions, right, in the proposed method that we see more than 80% of the congestion has come down. Similarly, in vertical direction, the congestion score has come down by 50%. And on an average, in both the directions, we see the congestion has improved more than 60% over here. Okay. And when we say the congestion is improved, obviously, in turn, it improves the design routability, where if you see here, right, 900 shots has come down to 150 shots, which made our life easy to converse the partition in a less time. Now, coming to the timing summary, which is most important in the VLSI design. So, if you see here, right, we started with a pretty high WNS path, and finally, with this approach, the WNS has come down to 80 PS, where we have to do our physical design tricks to meet this path. But the most important thing, what these paths are getting affected by the crosstalk, that is getting nullified here. So it's easy for us to fix these paths with the latest approach. And TNS also has come down all the way from 118 NS to 13 NS. We see a good improvement, and the number of paths to deal with has also come down significantly. And the turnaround time to close these partitions has also come down significantly. So the conclusion is the proposed approach can be used to enable SoC feed-through wise, even though the MIB, even through MIB instances. This approach covers the best possible arrangements of MIBs and the corresponding pin creation and placement, which in turn helps improve the timing and routing of the design. The successful adoption of this approach will enable SoC feed-throughs to avoid the presence of inefficiently used channels, optimizing the area utilization of the SoC. Yeah, thank you for giving us this opportunity.